exciting lecture on Sobolev spaces later on, right?
I hope so.
Well, yes, it's too bad that they're scheduled at 6 p.m. Otherwise, I would like to come, but I have the kids at home. So let's. I told Victoria and I told Lucia and Tariq to maybe see if the other ones can be a little bit earlier. Let's see. So let's continue, everyone. This is our functional analysis 2019. This is lecture 16, if I'm not mistaken, right? So we're going to talk a little bit about, LP spaces. Let's continue our conversation on LP spaces. So who is here thinking of taking the PDE class after here? Or at least 3. Okay. So you two? Some who was not here is also thinking, maybe 4. Yeah, because this is something, given what you have learned so far in functional analysis, I would suggest that you take a look at the PDE class. I would, strongly encourage you to take it, but if you're not unsure, please at least take a look, because some of the things that we're building up here are going to be applied there, and you will see some nice applications and so on. And I had a nice conversation with the professor of the class, Giovanni Bellettini, today. We aligned a little bit on what I'm going to finish doing here in this course and what he's going to start doing on PDE. So the plan for perhaps the end of this course, we have 5 more lectures to go, including this one, would be to talk still today a little bit about the dual of the LP spaces, like we started in the last class. This pretty much gives you a very good idea of chapter 4 of Bresis, given that we have talked extensively about convolutions and approximations of the identity and of the basic properties of Banach spaces, the LP as Banach spaces in the beginning of the class. Then I want to move a little bit towards Hilbert spaces and do the chapter 5. And then perhaps a little bit on the theory of the Fourier transform, Fourier series, Fourier transform, and so on. And probably I won't have time to talk about compact operators in chapter 6. This is something that you can take a look later on your own. Let's see. Where were we, everyone, in the last class? We had proved that That the dual of so we had proved this following fact, right? So fact 1 was that LP, when LP is reflexive for 1 less than P less than infinity. Moreover, we have seen that the dual of LP can be associated to the LP prime. This is isometrically isomorphic to this space. Good. We have also seen, so this is in the sense that every, remember, right? So every function of phi in the dual of LP can be associated to a function, say u on LP prime, such that this function of phi acting on any function f is actually given by the integral of u times f for any f. Right? Moreover, the norm of this function in the dual is the norm of this function. So really, this space here is isometrically isomorphic to this one. And we have seen this. We have constructed, say, a bijection going from this space. We have constructed a map going from this space to the functionals on LP, which is just given by integrating against this function in LP prime. It is linear. It is bounded because of Holder's inequality. We proved that it's an isometry, and then later we prove that it's surjective. This is one of the highlights. So this is as far as the discussion on the reflexivity property goes. We stopped here with this Rees representation theorem, and then we talked a little bit about the separability, right? We have seen that LP, say of Rn, of Rd, or generally LP of some sort of, say, dome. This is separable for 1 less than p less than infinity. Here I'm taking a domain of Rd, let's say an open set, or something with interior, not empty. Oh no, this is really any sort of domain. But then at infinity of Rd, this is not separable. Right? Perhaps other spaces that you can also think of that you would consider that are separable spaces are spaces of continuous functions, say of compact support. So if you take the continuous functions on the interval 0, 1, you have already seen that such a space is separable, right? So if you wanted to say, if you get the continuous functions on the interval 0, 1, say taking real values, you can approximate by polynomials, by the Stone-Weierstrass theorem, and then every polynomial you approximate by polynomials with rational coefficients. And then you're done. Okay, so there are some spaces of continuous functions that you can argue by the Stone-Weierstrass theorem that are separable. The fact that an infinity is not separable is because of the nice argument we constructed in the last class, that if you can actually construct an uncountable family of open sets which are which are disjoint, right? So you can construct an uncountable family of open sets which is disjoint. So this forbids the space to be separable. Okay, so today I want to resume the conversation on the duals of LP. So I want to study a little bit the dual of L1 and the dual of L infinity. Okay, so bottom line that we want to prove is that still we want to prove this thing, so that L1 dual is L infinity. So this theorem here will still hold, but L infinity dual will contain L1, but it won't be equal. Let's just say contain, but it's different. No. Okay, so again, the L infinity is going to be the dual of L1. The dual of L infinity will be the bidual of L1. There is a copy of L1 in the bidual, so therefore we're going to show that this is L1. Okay. So there's a copy of L1 inside its bidual, but this will be in fact not the whole story, not the whole thing. So this will show that L1 and L infinity are not reflexive. Okay, so this implies that L1 and L infinity are not reflexive. Okay. Let's see. Let's first start with the dual of L1.
Just for curiosity, does it make sense to stay taking duals, and this will not stabilize there?
Say that again. Does it make sense to?
Take duals, just time like an iterated duality, something like that, and that this process that never stops.
Well, if your space is reflexive, of course it will stop, right? So you have just the guy and the dual, and then things will be the same. If the space is not reflexive, yes, it may happen that you keep, not sure if the sequence would ever stop. But Most likely not, because if it's not, you could start coming back. But not usually sort of questions that one would be interested in, I suppose. Let's see. Let me just state the term that we want to. So this is the second part of research presentation. So let's see. Here. As before. So let phi be a guy in L1 dual. Then there is a unique U in L infinity such that phi acting on F is actually equal to the integral of U against F for every F in L1. Besides, moreover, the norm of this phi in the L1 dual is actually the norm of U in L infinity. Okay? Such a map is an isometric isomorphism, and henceforth we identify the, say, L1 star is going to be L infinity. Okay, it's isometric isomorphism. Okay, so let's prove that the dual of L1 is L infinity. Let's see if we can get some insight of the previous proof. So remember the proof that we did before, right? We constructed a map from LP to the dual of the other guy. We proved that it's bounded, linear, injective. And for the surjective part, that was the real deal. We had to prove that such a mapping was surjective. We somehow invoked the fact that the image was a closed subset. So the image through an isometry is a closed subset on the other side. And we used the fact that the closed subspace of a reflexive space was also reflexive. Okay, so this played a role. Okay. So if I want to do that here, this is where this proof would break, and we have to find a different argument. So let's try to start with the same as before. So proof. How would we start such a proof? Well, there is a natural map, say from this natural map T from L infinity to L1 dual, which is what it should be, right? I will send a function here U into a function which I'm going to call TU, and I have to tell you how TU acts on functions in L1. So I will just say that TU acting on F will be just the integral of U times F. Okay? So by holder, so this is obviously linear, no question about it. Let's check that. This is also bounded. Right? This is bounded. Why is that? This is just a consequence of holders inequality. Well, not even holder, but holder in the most basic set, right? So integral of U times F is certainly less than or equal than the infinity norm of U. This is just taking the supremum out times the L1 norm of F. So in fact, this actually defines this inequality here defines a bounded operator on L1. So therefore, T of U is actually an element of the dual. T of U is linear and bounded. This is one case, right? So it's one case to actually check that TU is actually linear and bounded on L1. So therefore, TU actually belongs to L1 dual. Okay? So the map is well defined. I'm mapping somebody here into somebody actually that is here. That's okay. It's another fact to check that the map T is linear. If I take just U1 and U2, it will just add up. That's okay. And also T is bounded, because the norm of TU by this thing in L1 dual is less than or equal than this constant. Okay. So this means that the map T from this space to this space is bounded. Okay, so this is check, check. And also this map T is injective. Let's see why this T is injective. We can try to prove it's an isometry, like the other case, to prove that it's injective. We could do that. But let's try to see it directly. So if it's a linear map, suppose it's not injective. So suppose that the sum T of U is 0, with U not 0. So this would mean that the integral of U times F is 0 for any F in L1. Yeah, so here
we can talk a localized function about
For example, we have approximate, for instance, with the bounded support, compact support functions.
So the fact that UF is 0 for any F in L1, so I'm saying that if this is 0, well, remember, here we are always assuming that our space omega is the union of, say, omega n's with the measure of each omega n being finite, okay? So I'm assuming that my space is sigma finite. So I'm working on a measure space omega, which is a union of sets with finite measure. For example, RD, okay? If you want to think of the Euclidean space, you can think about more general space. So the thing that you want to do is say, if you say that xn is just a characteristic function of the set omega n, so one thing that you can put in this expression is just take f to be, say, the characteristic function of this set times the signum of u. Meaning that all my functions are real valued, the signum of u is 1 if u is positive, it's minus 1 if it's negative, and it's 0 if it's 0. So when you do this, so this implies that this function is in L1, this function is integrable because this set has measure 0. This set has measure finite. So this f belongs to L1, and this thing means that then the integral u times f would just be absolute value of u integrated over this set, omega n. This is 0. So this means that u is 0 on omega n, but for each omega n, since they cover the space, so this u has to be identically 0. Okay? So essentially, if you were on RD, this is essentially proving that u is 0 in each ball. Therefore, u is 0 almost everywhere. When I say u is 0, of course, I mean 0 almost everywhere. Good. So this is one way to prove that it's injective. Of course, you could go the way that we went before and say, well, Emmanuel, you know, this thing here, this norm, is not only less than or equal, but it's actually equal. So it's actually an isometry. You could actually, okay, this is check. Let's check also that it's an isometry. If you want. To check that this is an isometry, what you would have to do is, you would do the following. Remember what we had before, right? So remember that if U was in certain LP, and we constructed this map, TU now belonging to LP prime dual, just by integrating u against f and f in LP prime, right? So we had to choose a particular function f to prove that this is actually not only less than or equal, but bigger or equal. And the choice that we had was f like u to pi p minus 2 times u, for example. Okay? So, well, when p is infinity, you can just not do this exactly like that. So you have to be a little bit careful. Okay? So this previous argument does not work exactly as it was before, but nevertheless, there's no big problem with that. So all we have to do is to make f and u resonate, to make them talk to each other, right? So if we want to make, remember, if we want to make this big, if u is given and you want an f, say of norm 1, to make this big, all you have to do is to make f talk to u, in the sense that they have the same signs and everywhere. So it's not such a big deal. So, but remember, your f has to be in L1. Okay? So if your function u, suppose if you were in the real line, if your function u in the real line were constantly equal to 1, you cannot take f, say, equal to 1 everywhere, because it is, say, not bounded. It's not in L1, right? But if your function is, say, like this, so you cannot take f to be equal, but all you have to do is just to take f to be talking to you in the sense that it's big on a set where u is big. So let's see how we write this. So one way to do this is that, okay, so let, say, c be any number which is less than the L infinity norm of u. Let's assume that the L infinite norm of u is not 0. Of course, if u is 0, p of u is 0, and then it preserves the norm. Absolutely. So let's assume that the L infinity norm of u is bigger than 0. Let c be any number which is smaller than that. Then, so if c is less than the L infinite norm of u, so there exists a set. So let's say, then the set, let's call it xc, just being the numbers x in your omega space such that u of x is actually bigger than c. This set has positive measure. Has positive measure. Okay? But at this point, it could be infinity. Okay? Potentially infinity. So just go ahead. So just choose a certain y contained in the set xc with finite measure. Okay, so such that the measure of this y is just positive and it's not infinite. Okay, so this set here has positive measure. It can be infinity, but then you don't want to deal with the function that's measure infinity. Just take a subset that has finite measure. You can just take intersections of its xc with these guys until you get something positive. You have to get something positive because this guy's over the space. Okay, and at the same time, these guys have finite measure. So once you get something positive, you get something less than infinity. Now, okay, so now you have a set where u is bigger than c and of finite measure. So you can just take now your f to be the characteristic function of this set y times the signum of u. Okay, this is certainly a function that belongs to L1 because the set has finite measure. Okay, so when you do the equation, on one hand, the integral, on one hand, say your t of u acting on f has to lose to the norm of t of u in L1 dual times the norm of f in L1. Okay? Which is equal, this is equal to norm of TL1, L1 dual. What's the norm of this function f in L1? This is norm 1, because u is not 0, it's bigger than c, right? So this is just a measure of your y. But on the other hand, this is equal to the integral of u times f. And the integral of u times f is just equal to the integral of absolute value of u on this set y. And absolute value of u is bigger than c. So this is bigger than c times the measure of y. Now you go from here to here. Boom, 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 boom. You cancel this guy because you can, because it's not 0 and it's not infinity. And you get an inequality that the L1 dual norm of TU is bigger or equal than C. But C was any C less than this guy, so this is bigger or equal than this guy. This is the contrary inequality of this. Okay, so since this holds for any C as above, any C less than infinity, this implies that TU in L1 dual is actually bigger or equal than infinity. Hope you can read this line. So this is actually the opposite inequality as this. So now you put together this with this, and you get your isometry. So with a little bit slightly different proof than what we had before. And again, the idea is not a problem. The idea is just to make f talk to u, f to be big where u is big, because u is attaining the norm roughly on this thing. So you just want to make f, your whole mass, concentrated where u attains the norm. This is just the idea behind that. Okay? Actually, this is, if you think about it, this is actually intuitively simpler than the LP case, because when you had a function u in LP, you know, if I want to make equality, this Holder's inequality, if u is in LP, I have to get f in LP prime that talks to u everywhere. But now if you want to make equality here, remember, I'm just pulling this constant out of the integral. So if I want to make this an equality, all I have to do is make sure that I'm putting the constant out where the whole mass of f is concentrated. So I'm just concentrating the mass of f in the place where I'm putting this constant out, which is essentially what we did here. Okay? Okay, you cannot just take the C to be equal to the norm of u, because then this set could not be, it doesn't have measure 0, so this is a formal way of doing things. But the idea is very simple. So we are at the same position that we were before. We proved that this map from this space to this dual is linear, bounded, injective, and it's actually an isometry, so if we had not proved that it was injective, it would follow from this fact. Since we prove it's an isometry, it implies that it's injective, so there's a different proof of the injectivity. What remains is for us to actually prove that it's surjective. Okay, so let me erase here. So the hard part of this proof, so let's say the new part is to actually prove the new part here, or the different part is to actually prove that this T is surjective. Okay? We already know that this T of L infinity is a closed subspace of this guy. But since we don't know information of the dual of L1 at this point, we cannot proceed as we had before. In fact, this space L1 will not be reflexive, so this dual will not be reflexive, and we cannot conclude that this guy is reflexive. But, so we have to proceed differently. So let's prove that T is surjective. Okay, so now let's do the following. Now, okay, so let phi belonging to L1 will be given. And let us construct such U. Let's construct a U such that T of U is this phi that was given. And the idea behind this is, again, to actually capitalize on what we did before. So we already know that LP between 1 and infinity is a reflexive. We have a very precise description on what's the dual of LP when you are between 1 and infinity. So let's try to capitalize on that. So we are going to do the following. So let's just do omega being a union of guys with finite measure. Okay, so let's just say mu of omega n finite. This is just the hypothesis that my space is sigma finite. Okay? With such a covering, you can actually find, if you want, a union which is disjoint. So you can, let's just say omega 1 prime is just omega 1, omega 2 prime is just omega 2 minus omega 1, and then omega 3 prime is just omega 3 minus omega 1 union omega 2, and so on. So you just take at every step the complements. So you can actually write your omega as union of let's say, primes. So for all purposes, we can also say that these guys are all disjoint, if need be. All of these guys are infinity and all disjoint. Okay. So not to be working with the primes anymore, so let's just assume that my first decomposition, all the guys are disjoint. Okay, so if we need, we can assume that these guys are disjoint. But what I first want to do, okay, so let us assume that gamma is union of gamma n. This is measure of omega n finite and disjoint. So my first claim, so let's say claim 1 or fact 1. Let's just divide this in different facts. So fact number 1. So this we'll divide this proof of the surjectivity in several small facts. So fact 1 that we can do is we can actually choose. So we can choose. Remember this. We can choose a function v. So what do I want to say first? What do I want to say? Okay, choose such a function v. With, let's say v in L2 of omega. Let's see if this is correct. I want to choose a function L2 of omega such that v of x is bigger or equal than a certain quantity. V of x is equal to a certain quantity, say alpha n bigger than 0 on omega n. So my function v is always bigger than 0, and it's going to be alpha n on the set omega n. So these sets are disjoint. Okay, so I can choose non-negative constants alpha n, such that if I place a function to be alpha n on each of these sets, which are all disjoint, I get a function which is L2. Okay, so if I want to make the function in L2, the only thing I have to choose is what? is that the integral of v of x squared in the whole thing, I want to choose in such a way that this is finite. But this is just going to be the sum of, so if it's constant equal to alpha n in each set, it's just going to be alpha n squared times the measure of mu n, right? So these measures are finite measures and they're given, so you just choose the alpha n such that this converges. Okay? So if you want, for instance, you may choose alpha n to be 1 over square root of these measures. Let's just assume that they are all positive measures, because otherwise I just remove this from this thing. So let's just assume that all measures are positive. And then perhaps 1 over n. And you have, this will cancel with this. Huh?
N squared?
Well, alpha n will be squared here.
Ah, okay, sorry.
If you want to even.
Sorry.
So this is something that will make this function belong to L2. Okay? Alright. So good then. Okay, so this is fact 1. Now my fact 2. Now I want to construct what should I do here? I want to take advantage of this function that I just constructed to construct a map, a function in L2. So consider the following map from L2 of omega to R. And the map is going to be the following. I'm going to take a function g in L2, and I'm going to send to phi acting on v times g. How about that? Remember, my phi was a guy in the dual of L1 that was given. So I'm now proposing to you to take a look at this map that goes from L2, takes a function in L2 and sends to this number, phi acting on this. So first of all, notice that v, your v here, belongs to L2. So if you take a function g that is in L2, v times g belongs to L1 by Holder's inequality. And then you're applying phi to an L1 function, which is good. So this map here is such that phi acting on v times g is less than or equal than this number, which is just a number, times the L1 norm of v times g, which is less than or equal than, again, this number, times the L2 norm of v, times the L2 norm of g. This is just a number, this is just a number. So I'm taking a map that sends me, I'm getting an operator that gives me a function g and sends me to a real number that is bounded by the L2 norm of g. Of course, this map here is linear, so it's a linear unbounded map. So this map here, if you want to call it phi, I don't know. So this map phi belongs to L2 dual. So it's a linear functional on L2. It takes an L2 function and maps it to a number in a linear and bounded way. But we already know what's a function in the L2 dual. So we already know, so we have already, therefore, hence, we can then find a certain f that belongs to L2 of omega that represents this guy, okay, such that, let's say, phi vg is actually just the integral of f against g. Okay? And you see what I'm going with that, right? So again, this map here that sends g to this number, this is the functional phi of g that I'm calling, right? Is represented by a function in L2 by an integral, right? So the integral of f against g. This is the representation theorem that we proved before. For any LP, we're using the simplest case of L2. So you see where I'm going with this. So I'm almost done in the sense that I am applying here phi to Vg, and I'm getting that this is f times g. So at the end, remember, I want to actually prove that phi with any function h is just u against h. So what I will do is actually, if you look at this size correctly, you can just say divide by v and multiply by v here. So you have the phi applied to somebody. It's just this function applied to somebody. Okay? And this is actually the function that we're looking for. And here, hence the reason that I'm choosing this v to be always positive, so I can actually divide by v. Okay, so this is...
So can you repeat this again about v?
So we have produced this f.
Yes.
So in principle, it seems a bit artificial that we are kind of introducing a v. The reason I'm introducing this v in L2 is to actually be able to capitalize on what we have already proved, this representation theorem for L2, right? So by introducing this v, I actually can produce, this is the nice step to produce a function that does an integral representation. So I have concluded that phi acting on v times g is equal to the integral of f times g. At the end, I want to prove that phi acting on any L1 function h is the integral of this u that I have to find times h. So if you look at this integral representation here, you almost see that phi acting on somebody being the integral of a function against the same somebody. But you see, I have vg here and I don't have vg here. Now, why not? I could have if I just say multiply by v and divide by v. So you would have phi acting on vg being the integral of a function times vg. Oh, so this would be a good candidate for your u. This f divided by v. Can you divide by v? Yes, because we chose this v to be known strictly positive everywhere. So this is, the pieces start to fall into place. Okay, so the claim, the next fact that we're going to prove, the claim is that u equals to f over v is our choice. Okay? Okay. What should we prove first? So let us first prove that fact 3. What do you guys want to prove first about this?
Is it infinity?
It's not clear first that this function is in L infinity, right? So let's first try to prove that it's in L infinity. Let's first see if we can do this. So let's try to prove that u belongs to L infinity. Okay. How do I prove that? In fact, let's try to prove, let's prove that the norm L infinity of u loses to this norm of phi. L1 dual. Let's see if we can do that. So to do this, let C be somebody which is actually bigger than the norm L1 dual of this guy. Is that what I want to do? Use an infinity. Let's see if we are correct here. I want to prove that U belongs to L infinity. I will actually try to prove that the infinite norm of U is less than this guy. So let's take C, any number bigger than the L1 norm. Okay, so let's investigate. So let us investigate the set, say A, which is the set of points x in omega, such that U of x, let's say, bigger than C. I do this, bigger or equal than C. I want to show that the measure of this guy is 0, right? This is what I want to show, that the measure of this guy is 0. Okay, and what I will do is what? What we will do is I will take first, so let me first, to prove that the set is 0, so we must show.
Why can't we use Chibichy?
Where?
This
Wait.
for to calculate the measure of A. Because we are starting with that U is in L1, right?
I'm starting with U in? No, U is not in an infinity.
No, we don't know. But we cannot.
F is in L2 and V is in L2.
Ah.
That's all I have.
How we do the measure of this A intersected with omega?
Yeah, so we must show that the measure of A is 0, and it suffices to show that the measure of A intersect any of our omega n's is 0. Do you guys agree? Okay, now let's try to see why this is reasonable. So remember, I can apply this to any function g in L2, right? I can apply this to any function g in L2. So what I will do is I will take, let's see if this works. So let's take g there to be the characteristic function of, so let us denote like by key n is the characteristic function of this set, omega n. So this is key n of what? Or key, let's say A intersection omega n. This is just a characteristic function of this set. And what we want to do is I just want to put divided by V, right? Can I do that?
But usually we are not guaranteed this in L2.
I am, right? This is just one, and this is just a number.
And omega n
This in omega n is just a number, alpha n, right? So this is just a constant function on a certain set. So let's just take this. So let's say if I got this correct. So if I got this correct, this would be phi acting on, and then v times g would just be characteristic function Ra times omega n. Okay? On one side. On the other side, this is the integral of f over v times vg, which is just the integral of my u times vg is just the characteristic function of a such omega n. So maybe I want to put here also the signum of u, maybe. Let's just put the signum of u here. Okay? So this is this times this, so divided by v. Because when I put the signum of u, I get vg is to be equal to, well, f over v is u, so I get here the absolute value of u. Now, on one hand, there is a quantity that is bigger or equal than this, right? Which is the L1 infinity norm times the L1 norm of this function, which is just the measure of A intersection omega n. And on the other hand, this is bigger or equal than U on this set is bigger or equal than C, right? Times the measure of A intersection omega n. Okay?
There's something, so B missing
But
on the left side,
B where?
in the left side,
Here?
over, yes, omega n intersect omega n over B. No, so, okay, sorry, I mean, it's okay.
But remember, C was somebody bigger than this guy, right? So the only thing that this number times this is bigger than C times this. So C times this number, well, so this implies that this number here has to be 0. Otherwise you have a contradiction. You could cancel, and then you would get a contradiction to this fact. So this implies that measure mu of A intersection sigma n is actually 0. Good, right? And we are done with that. Okay? So this proves that mu of A is 0. So the measure of the set A, where u is bigger than C, is 0. This holds for any C bigger than the norm. So the L infinity norm of u has to be less than or equal than the L1. So our function u that we constructed here, that in principle was just the quotient of two functions in L2, we proved that it's in L infinity. Okay, so this is starting to look more like our candidate. It's actually a function in L infinity that we wanted. Good. Okay? So what's the thing that I have, what's the final thing that we have to prove? We already proved that it's an infinity. We have to prove now that, okay. Is that okay? I'm very glad that I still know how to do this. Let me erase here. We already proved that our function is now infinity. So the fact number 4 that I want to show to you is that
Is a pre-image of our function.
in fact, so I want to show that for let's see if we can prove this. For any h in L1, now let us show. So let's show the conclusion that the phi acting on h is actually equal to the integral of u against h. I already produced an L-infinity function. This u is already an L-infinity. Now let me show that it's the function that we're looking for. That for any function in L1, the function of phi that I gave you in the beginning, acting on this h, is actually the integral of u against h. This will conclude the proof. Right? This will conclude the proof. Okay. So now it's the moment for us to just do some basic simplifications, because all we know is this relation here star. So this relation here star holds for any g in L2. Okay? So it's almost like what you want to prove, but it's not exactly the same. So I'm allowed to apply phi to, I'm allowed to use my integral representation with v times g, where g is a function in L2. So I guess what you want to do here is to, now your function h is in L1. So the problem that you have is that you may not necessarily have this h going to L2. So you have to do some truncations here, it seems, right? So the problem of a function belonging to L1, not in L2, sometimes it's because it's too high. So if a function h is 1,000, then h squared would be 1 million. So if a function is bounded above, if your function is bounded above and it belongs to L1, then it belongs to L2. So to deal with this, so let's say for each natural number n, let us truncate h by considering, say,
Minimum is n.
by considering, yes, the minimum with n. So let me consider hn of x, which will just be h of x. Let me write, perhaps in a big line. So I will just consider hn of x being h of x if absolute value of h of x is less than n. And I will just say that it's n if absolute value of h of x is actually bigger than n. I'll not put n because my functions might be positive or negative. So what I want to do is that just take my function h, and I want to say to truncate at a certain level. So whatever is above, I will just substitute by this, and whatever is below, I will just substitute by this. So this is not n, this is just n, let's just say n times h of x divided by the modulus of h of x. That's just, if h is positive, then it truncated n, if h is negative, it truncated minus n. So this is just a truncation. Just put the lines n and minus n and cut your function, okay? So now, obviously, with this construction, your hn of x is obviously bounded by n. Good. What else would I like to do? This doesn't, well, each of these belongs to L2, you're correct. Each of these belongs to L2, right? Because now it's bounded. So if h belongs to L1, this belongs to L2. It means that I could potentially plug in here, right? So let's see if we can plug in there and find something meaningful. But still, I want to apply to this h. So let's see. So I wanted to say phi applied in hn, okay,
maybe we divide by v to.
Yes, but then when I divide by v, so phi applied to hn, this is what I want. This is now a function, say, in L1, okay. And this is phi applied. If I want to use that expression, I have to put v and hn over phi. Now comes a little bit of a problem because if I divide by v, this function here is the g that I want to apply. This does not belong to L2 because if my v's, they are positive, but if they get too small, this might get too big, right? So let's do another truncation. We did already truncation in the size. Now let's do a truncation in the domain in order to not lose control here. So let's go ahead and let us also define I don't know, give it another name. So H, and let's call the
Maybe we make sub and the lower indices.
Oh, we're just gonna call, I don't know, maybe HN, maybe truncation N, HN, or maybe not, that's maybe. Let's give another name. So I use G, I use H, let's call big H, HN, X. It's just the characteristic function of the set omega n times Hn of X. Okay, so we truncated in the height n and we truncated in the domain by multiplying by the characteristic function of omega n. So these big functions, big H of n, they are now everything that you want them to be. So you want to start with phi acting in your big H n. This is fine, right? Because you know this little h loses to that h which is in L1. This is just a truncation in the domain, so it's certainly in L1, so you can apply phi to an L1 function. That's fine. But you can write phi as phi acting on v times hn over v. Okay, so now you multiply and divide by v. There's no problem in doing this because your v is never 0. That's fine. Now, this function here belongs to L2. Why? Because this little h was bounded above and below by n. So this little h already belonged to L2. And you're dividing by something which is just, it's not, well, yes, okay, it's constant in omega n, right? It's just a number. So this is certainly a guy in L2. Okay, so you have phi applied to v times a g in L2. Now here's the step that you apply star. And this is equal to the integral of your f times this function g. All right?
No, there is no v.
I'm sorry, f times your function g. And, okay, obviously this is, if I just group these guys together, it's going to be the integral of u times hn. Okay? Now I want, so this is just a chain of equalities. What I'm left to do is just, I want to use the dominated convergence. So I just want to use that Hn converges to H in L1. Not only converges, but it converges by below. It converges to H in L1 and Hn of X is always less than or equal to H of X.
This second part is by construction.
This is by construction, right? Because I am this Hn, I'm cutting at the level n, and I'm also cutting in the domain. So every time, at every n, I increase the domain in the bottom and the domain in the top. So they are converging in L1 from inside, if you want. So it's always less than an absolute value. So I'm going to apply the dominated convergence on both sides.
Maybe we need to take Hn again, and Hn converges to H, this converges to this, because we have this is Hn, right? This.
I could have divided with two indices, n and m, but I'm already taking the same n. I'm taking diagonal, okay? So I'm doing the two slices at the same time. But yeah, if you wanted to truncate in n and then truncate in m and then send m and n to infinity, you could do that as well. Okay, so all that is left is to use dominated convergence. I have a chain of equalities here. This thing converges to phi acting on H just because this is a guy in the dual, and this function converges to this function in L1, and this is a continuous functional. So if I get something that converges to this, so this is just from the fact that phi belongs to L1 dual. And this fact here, this converges to, now you have a function u in L infinity, and Hn converges to H in L1, dominated. So here I apply dominated convergence to guarantee that this goes from to 1 against H. And voila, phi applied in H is just the integral phi applied. This conclusion. All right? All right, we have a few minutes. Questions or comments? This is a very nice proof, very interesting. So still you have that the dual of L1 is L infinity. The thing that makes L1 and L infinity not reflexive is that the dual of L infinity is somebody that contains strictly L1. Are we good with this? Okay, so first let's finally discuss this example. So let me let's see, how do I want to do this? Well, let's see. Okay, so I want to present you the following proposition. L infinity dual contains, and it's not L1.
If L1 is reflexive and we know L1 separable, L infinity is reflexive and separated contradiction.
Yeah, so yeah, remark, in particular, say L1 and L infinity are not reflexive. But that, still, one of the nice things is that L infinity is the dual of L1. So being a dual space, we already seen in the previous chapter that being a dual space has nice properties. For example, the unit ball in L infinity is weak star compact. So it's compact, the topology given by the functions of L1. Banach-Loglu theorem we can apply here. And L1 is separable. So yeah. So
reflexive.
no, L1 is not reflexive. Yeah.
If L1 is reflexive, so in this case L infinity is also reflexive and separable, but L infinity is not separable. We proved this one. Because reflexivity and separability implies again
Yes.
reflexivity.
Oh, but you don't know that L1 is not reflexive anymore. So what you're saying? So you're offering a proof of this proposition?
No, I said L1 is not reflexive. We proved that, so L infinity is.
No, we haven't proved that yet.
Because if L1 is reflexive, we
Okay.
assume that L1 is reflexive, so we
And
know
separable?
it's separable,
Yeah.
and L infinity again separable. But it's contradiction because of this L1 is not reflexive.
Okay. Okay. So this is one possible proof. So what you're saying is that proof of this proposition is that so if L1 were reflexive, but then this would be a proof on RD, right? L1 of RD. Okay, so you could argue like this. You could argue, or any sort of, say on RD, or spaces of sequences, if you want. So we have seen that L infinity is not separable. We have seen that L infinity is not separable. So if L1 were reflexive, so we have seen that L1 is reflexive plus separable. This would imply that L infinity, which is the dual of L1, would be reflexive plus separable, but L infinity is not separable. Okay, so therefore L1 is not reflexive, and the proposition holds. Okay? Okay, so this is a perfectly good proof for the cases where you know that L infinity is not separable, namely on any sort of domain of RD or spaces of sequences, we're fine. Let me say in general, let's say if we wanted to work with L infinity of any sort of domain, any sort of measuring space omega, one possible way to proceed would be to use the fact that a convergent sequence, a bounded sequence, has a weakly convergent subsequence. So let's try to explore this fact. Let's see. So in here you would have two cases, right? So case one, there are two possible things that may happen if you're working in a general measure space. Either for any epsilon bigger than 0, there exists a set, let's say omega epsilon, with the measure of omega epsilon less than epsilon. Or case 2, there exists an epsilon bigger than 0 such that if measure of a set omega is less than epsilon, it implies that measure of omega is actually 0. So it may happen that in your measure space you may have sets with arbitrarily small measure, or it may happen that there is a threshold that no set has measure less than epsilon. Okay?
But if our space is sigma coordinate, we can always take a point, right?
Well, for example, the counting measure on the natural numbers, the space of sequences, is a space of case 2. No set has measure less than 1. Okay? So we essentially have these two cases. Let's do this case 1. So in this case 1, what you can do is that you can construct a decreasing sequence of sets whose measure goes to 0. So let us construct, so you can construct sets, say omega n, with, let's say, omega 1 containing omega 2, containing omega 3, containing blah, 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 and the measure of omega n is going to 0. So it's very simple to construct a decreasing sequence of sets whose measure goes to 0. So one potential way to do this is just hint how to do this is to just choose any sort of set, say an with measure say less than 1 over ak 1 to the 2 to the k, which is guaranteed by this case, and write omega n as just the union of the ak's with k bigger or equal than n. So something like this. Okay. So you found a decreasing sequence of sets. Yeah, so this is to show that what? The L1 is not. Okay, so suppose what I want to do, suppose that L1 is reflexive. Suppose that L1 is reflexive. And you consider these functions here, say fn is to be the xn over the L1 norm of xn. Xn is just the characteristic function of the sets. So let's just take fn to be key n divided by the characteristic function and the L1 norm. This is like these sets. What you're making is that fn has norm 1. If this were reflexive, we know that there would be a weakly convergent subsequence. Right, so there would be a G belonging to L1 with, let's say, F and K weakly convergent to G. Let me just drop the K and just consider the sequence itself. There will be a weakly convergent subsequence. Okay? Just passing to a subsequence. So what I'm saying here is that if you are in a reflexive space and you have a bounded sequence, then there's a weakly convergent subsequence. We have already proved that the dual, so the sequence converges in the weak topology, the dual of L1 is L infinity. So this actually means that the integral of u against Fn is actually goes to the integral of u against G for any u in L infinity, which is just the dual of L1. For any guy in the dual, we have this convergence. Okay? So let's see, how do we make a contradiction out of it? So I guess here we'll just choose, let's say, just choose this u to be the x, the key n. So when n goes to infinity. So what happens with the left-hand side, key m, when n goes to infinity? This goes to what? Key m, so if m is fixed, when I send n to infinity, remember, these functions have support inside each other. So at some point, the support of Fn will be inside key m, so this just be 1. The integral of Fn is just 1. Is that okay? Now, on the other side, so this means that this, and this is the, if this is fixed, when n goes to infinity, I already know that this goes to the integral of u times key. This goes to the integral of my u is key m times this function g. Okay. So if when n goes to infinity, if this goes to this, and this goes to this, so these limits must be equal, right? So the integral of key m times g is actually equal to 1 for any fixed m. Okay? But now you send m to infinity. When you send m to infinity, since g is in L1, g is integrable, These functions key m being a decreasing sequence of sets, they are dominated by g. G times key 1 if you prefer. Right? So by dominated convergence, this goes pointwise to 0. Because these sets, these functions here, and they go pointwise to 0 almost everywhere. And so this goes to 0, and then 0 cannot be equal to 1.
Why?
Well, if I have to explain that, and then we go back in mathematics for 2,000 years, right? I guess people at some point in time, they ask themselves, why is 0 not equal to 1? Well, I guess still today there are people that think about all sorts of questions in logic, I guess, right? I mean, these are very complicated questions. It seems that these are the most difficult questions in mathematics to discuss. I mean, if things like...
But the simple answer is, I don't know.
Yeah, this is always a very good answer. Yeah. Good, so this is another way to see, for a general sigma finite space, what small as possible sets with measure as small as you want. This is an example to show that that one is not reflexive. Therefore, the dual of L infinity cannot be L1. It has to be something bigger. Now, in the second case that I showed you, this is actually a very interesting thing. So the second case that I showed you was it what? Case 2, right? Mm-hmm. Case 2 was when there exists epsilon bigger than 0 such that if a measure of a set is less than epsilon, then the measure of a set is 0. In this case, I want you guys to show, and I will leave this as an exercise for you. It's very nice. To show that the L1 of omega is just isometrically isomorphic to this L1, little space of sequences in L1. Okay? And as we did here, so this space here, little L1, is not reflexive. And the reason that it's not reflexive is that, well, we can do the same sort of proof. We can let's see, let's just consider the sequences, say, En to be 0, 0, blah, 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 1, 0, 0, 0, 0, 1 in the position M. If this space, this is in L1, it has node 1. If this space were reflexive, if L1, this is not, L1 were reflexive, we would have the sequence En, or passing to a subsequence, weakly converging to a certain sequence F. Okay? And then convergence is in the weak sense, but we already know that the dual of little L1 is the L infinity. So now we take this sequence, say, Gm, which is just 0, 0, blah, 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 0, and then 1, 1, 1, 1 from the position M on. These guys are in L infinity. So the integral of Gm times Ln is a perfectly well-defined functional. This is, I'm sorry, En. So when n goes to infinity, this obviously goes to 1. M is fixed. When n goes to infinity, at some point it will enter in the range of 1s here. But on the other hand, it goes to, by the weak convergence, it goes to the integral of Gm times F. Okay? So this means that the integral of Gm times F is 1 for each m. And then you send m to infinity, since your F is an element in L1, reflexive it would converge weakly to another element in the space. But since your F is in L1, and when you send m to infinity, this has to go to 0. And this is a contradiction because, again, 0 is not equal to 1. Okay? So now send m to infinity. Okay? Good. Yeah, okay, so this is, I think, a good point. the rest of this chapter. If you want the concrete, so we have showed, for example, in an indirect way, that L1 is not reflexive. Either the proof that Kakinboy offered in the cases where we know it's separable, or in the more general framework module of this exercise. We have shown that it's not reflexive. Therefore, the dual of L infinity is not L1. So there are functionals on L infinity that are not represented by functions of L1. If you wanted, say, an example of such a function, say, well, this is an indirect proof, we proved that existed such functions. But if you wanted to actually put your hands on an example, what I would suggest is, maybe I'll take 2 minutes to just show you this nice example. It's just essentially the Dirac delta. Right, so if you want an example, so you may take the space, say, of continuous functions of compact support, say in RD. So you have continuous functions of compact support with the supremum norm. And you may consider the functional phi that acts on F just to be f of 0. Okay? So this is a subspace of L infinity of RD. This is a subspace with the supremum norm, with the L infinity norm, right? And this is a well-defined functional in this subspace. This is a bounded functional. It's obviously bounded. This is bounded by the supremum of F. So there's a bounded and linear thing. So there's a functional in this space. So by Hambana, say phi extends to somebody in the L infinity dual. So I can extend this to a function in the L infinity dual. And the claim is that there is no function f in L1, say of RB, such that phi acting on G is just the integral of f times G. So in fact, if this happened, we would have what? That the G of 0, or that, say, integral of f times G would be 0 for any. So there is no f such that this holds for all G in L infinity. In particular, if I just took any G with C infinity of compact support with G of 0 being 0, this would be 0. Okay? So now, if you tell me that your function f is in L1, and that the integral of f against G is 0 for any G of compact support and 0 at the origin, G continuous of compact support, it's not hard to conclude that your function f must be identically 0. For if you take any place outside the origin, you can approximate just f in L1 by continuous functions. We have already seen this. And then you can take it in such a way that you don't touch the support near the origin. So for every little ball outside of the origin, prove that f is actually 0 on that ball. So the only point that is remaining is at the 0, but then you don't care because then it's 0 almost everywhere in the Lebesgue sense. So, and then this is a contradiction, right? So if there existed f in L1 such that this happened, then the f would be 0, but of course this functional is not the 0 function. It's a very nice exercise if you have never done this, to actually prove this. Prove formally, you know? Just take your function, say f, so I want to show that f has to be 0 here. Just take signum of f and this little ball, do the convolution with something with very small support, and then they will support a little bit bigger, then send the epsilon to 0 in the approximation of the identity to recover the function in the L1 sense, if you wanted to argue like this. Okay, so this is, As an example here, this Dirac delta, if you want, the functional that just picks a point and evaluates the function at the point is not somebody that can be represented by an integral with f in L1. So this is an instance that you should actually look at the dual of L infinity is a certain space of measures, but it's kind of complicated to describe. It's more of a space of measures than the actual functions. These measures on this tool need not to be, say, absolutely continuous. It could have measures which are singular in a point, like the Dirac measure, for example. But conversation for more advanced classes. But let's stop from here. So I'm satisfied if we get the grasp on this topic. So we have discussed it in the previous two classes, reflexivity and separability of LP spaces. So by now you should know the dual of all LP spaces and when they're reflexive and or separable. In general framing or in RD especially. Okay? So next class on Tuesday, we start and talk a little bit about Hilbert spaces. Good everyone, have a good weekend. Let's finish here today.